All right, so go ahead and pause the video and read the example, okay? So this problem is all about constructing a confidence interval for a mean, and here's an important difference with a known standard deviation, okay? So this time, and this doesn't usually happen, we're gonna go over this here in just a second, but we are given the standard deviation, okay, for our population, okay? So let's run through one of these, finding a confidence interval with a known standard deviation. So just like before, we have to communicate. Okay, so we have to see, okay, well, what is our mu this time? Okay, let's see, where is this? The mean weight of all tomatoes in this farmer's field, so in his field. Okay, we're looking for a 99%, I could try that percent a little bit better, a 99% confidence interval, and we're going to throw that in the inverse norm to get a z star of 2.576. Okay, and a couple other important information or a couple of other bits of important information that we should write down. We have a sample size of 4. We have an x bar of 110. And we have a standard deviation of 40. And again, this part right here is what's not usually given to us, but it is for this problem to make it a little bit simpler for the start. Okay. All right, so moving on. Okay, check our conditions just like usual. Okay, got to check to see if it's random, and this was a random sample was taken. It is indeed independent. We'll write down our evidence for that too. Okay, because 4 is less than 10% of all the tomatoes in the field. Okay, and I would say that's a safe assumption. I would assume that the farmer there was growing more than 400 tomatoes. So safe assumption. Okay, so normal. All right, let me just write safe assumption before we move on. Okay, then is it normal? So let's see. Assuming the population of all tomatoes in the field is normally distributed. So there we go. That's our key. That's our nice little shortcut where we don't have to worry about the central limit theorem, which would not apply in this situation because our n was 4, which was less than 30. Okay, so we would not be able to use the central limit theorem here. Okay, so the population is normal. Okay, so therefore, our population, oops, sorry, not population. I'm thinking the wrong thing. So our sampling distribution will be approximately normal. All right, so it fits all our conditions. We can move on to our calculations. Okay, and so remember we have to identify the inference method we're using. So this time, and again, this is where things get like really, like you gotta memorize these things. This is a 1 sample z interval for means. All right, and I'll write down the formula one more time for you. We have x bar plus minus z star times standard deviation of the population over the square root of n. Okay, and when we plug in all of our variables, we're going to have 110 plus minus 2.576 times 40 over the square root of 4. Okay, which gives us an interval of 110 plus or minus 51.52. And then we could also write it as an interval, so 58.48 to 161.52. And then last up, we've got to conclude, and we can use the same script we used for our last unit. So when we're dealing with a confidence interval, so we are 99% confident that the true mean weight of the farmer's tomato plants will be between 58.48 grams and 161.52 grams. All right. So now let me go. Now let me go about like why do I keep talking about having the whole population standard deviation? Okay, because this is where the means get a bit tricky. Okay, so when we constructed this confidence interval, we made the assumption that we knew the true population standard deviation. Okay, and this is a silly assumption. Okay, it's a silly assumption that we should never make. Okay, so if we're creating a confidence interval to give us an interval of plausible values for that population mean, so remember, in order to find the standard deviation, we have to know the mean. Okay, so why are we running through this problem with this assumption of the standard deviation when we don't have any idea where the mean is at? Okay, so that's why most of the time, okay, you are not going to have a known standard deviation. Okay, most of the time it's going to be unknown, and that's where things change up a bit. Okay, all right. So when we do know, okay, so when we do not know the population standard deviation, we must estimate it from our sample using the sample standard deviation. So that we can find. Okay, we can find S. Okay, but when we do that, when we're using the sample standard deviation as our, sort of guess for the population, we can't use Z. Okay, so because it's changing up a bit. Okay, so we have to use a new test statistic. This is called the T statistic. Okay, and it has a new distribution associated with it. I'm going to go over that in just the next video. Okay.